All right, in this section we're going to look at multiplication and division algorithms and some of the other ways we can estimate and sort of do those operations in our head. Okay, so to start off with, we need to kind of remind ourselves of some exponent rules. Let's just start with this idea of what do we say when we mean a to the nth power. That means a times a times a, and total, we're looking at n of those. So when we say exponents, we're meaning that there's the same number times itself that many times in a row. Okay, so let's kind of branch this out just a moment. Let's say we've got a to the m power times a to the n power. Okay, that means we have, using this idea, we have m number of a's, m, the letter m, and then with the nth, we have n number of those. Okay, so if I combine them together, how many a's do I have? Well, that would be m plus n, which we can rewrite as a to the m plus n power. Okay, so it goes back to when you are multiplying variables that are the same base, you can add the exponents. Okay, kind of remind us of a couple other exponent rules. If I raise something, so if I take a number, take a base with an exponent and raise it to an exponent, then I can multiply the exponents together. If I have different bases, but they're being raised to the same exponent, I can do the product of the bases and then raise it to that power. Okay, another rule is if I'm dividing, so divide by the same bases but to different exponents, that's going to translate into subtraction, and of course anything to the 0th power is equal to 1. Be another rule that we want to look at. And then let's take a moment and let's practice these. So let me get some spaces that I can write on. Let's take something like 2 to the 6th times 8 to the 5th times 16 cubed. Okay, so your first thought is, what does that have to do with? This is no common base. However, I can rewrite 8 and 16 in terms of 2. So that's 2 to the 6th times. Well, 8 would be 2 cubed, and 16 would be 2 to the 4th times 3. And then we can apply that other rule that says if I multiply, so if I raise an exponent to an exponent, I multiply that out. So that would be 2 to the 15 times 2 to the 12. And then I can add all those together. So 6 plus 15 plus 12. And I should get, let's see, 2 to the 33. Okay, let's look at one with division. So 9 to the 4th times 36 to the 5th divided by 3 to the 18th power. Okay, again, do you notice that the bases are different? However, we're going to make them all say the same base. So I can rewrite 9 to the 4th as 3 squared to the 4th times, let's see, 36 would be, be 6 times 6. So that's, well, let's write that out so we can see it. 6 times 6 to the 5th divided by 3 to the 18th. Let's see, so that one would be 4, let's see, 3 squared to the raised to the 4th would be 3 to the 8th. And 6 times 6 is really 2 times 2, so 2 squared times 3 squared. that we're all raising to the 5th power. And then I can apply that rule that says I can kind of distribute that 5n. So 2 to the 10th times 3 to the 10th, all divided by 3 to the 18th. So what do I notice happens with that numerator? I'm sorry, with the first part, I got 3 to the 18th times 2 to the 10th, all divided by 3 to the 18th. What's going to happen to 3 to the 18th? Those are going to disappear on us, and we're just left with 2 to the 10th. So works out to be 2 to the 10th. Okay, so our first multiplication technique is called the partial products algorithm. Let me give us a problem that we can illustrate this on. So let's do 12 times 4, kind of see how that works. Well, one of the first techniques we typically try to look at is sort of a concrete model. So 12 times 4 says I've got 12, but I have 4 sets of that. Okay, and so what does that add up to? That's 40, and this is 2, 4, 6, 8, plus another 8, so we get 48, right? Another way we can kind of look at this, again, is 12 is really 10 plus 2, and we were multiplying that by 4, so 4 times 2 is 8, plus the 4 times 10, which is 40, and notice we still get 48 again. Okay. Now, the way we would typically see this written out is we just 4 times 2 is 8, 48, and then we call it a day. But each of those methods has their own value, right? Let me fast forward in time to say something that they might see in algebra. What are we illustrating here? I'm saying I've got 4 groups of, so we would say distribute that in and get 4x plus 8. But notice, isn't that the same as 4 times 10 plus 2? So 40 plus the 8, the same way of looking at 4x plus 8. Okay, so let's take a look at, so this next technique is multiplication by powers of 10, or 10 to some exponent. Let's start off with something simple like 23, wow, let me try that again. 23 times 10, okay? So what that would map to, let's take a look at the number 23. 23, you know, we've got 2 of the groups of 10, and we got 3 singles. Well, when I multiply it by 10, each of my longs become a box of size 10. So this becomes 100, this becomes 100, and each of the singles all become a row of 10 themselves. So what do I have here? Sorry, 10, 10, and 10. I have 230 units. So I can concretely see what's happening there. Okay, so with 2-digit factors, let me give us something we can work with here. So let's go 23 times 14. Okay, this is, I guess, the method we're sort of used to. We would start with the ones, so 4 times 3, we get the 12. We carry that up, so that'd be 9 here. And then this is really 10 times 230, or 10 times 23, so we get 230. And then we can add those. So that would be, carry the 1, so 322 would be your answer there. But that would be organization, but let's look at other techniques. Okay, in the lattice method, let's look at that same 23 times 14 problem. I'm going to make a box, and I'm going to put 1, 4, and 2 and 3 there, and then each box I'm going to split in half. Okay, and then I'm just going to multiply like I see. So 4 times 2 is 8. 1 times 2 is 2. 4 times 3 is 12. And 3 times 1 is 3. Okay. And then I'm going to add my diagonals together. So starting in the bottom corner, I get a 2 there. Then I have a 3, 1, and 8. So that's 12. So I'm going to carry the 1. I'm going to put a little mark there. And that'll put a 3 there. So I get 322 with that. Okay, so we're going to look at division algorithms, and this first one we'll look at is called repeated subtraction or partial quotients. Let me give us a problem that we are doing. So 6 into 726, and I'm going to start with the fact that I know I can get at least 100 in there. So if I look at 6 times 100, I can take out 600. Leaves me with 126. And how many groups of 10? Well, I can get 60 out. That's another 66. I can get another group of 60 out, which leaves me with 6. How many groups of 1 can I get out? Just the 1. Right? So how was that? There was one group of 100. There were 2 groups of 10. And there was one group of 1. So it went in there 121 times. Okay, so let's look at that same problem again, but let's do what's called the scaffold algorithm. So 6 into 726 again. Let's see. So sort of the same idea, just how we write it is a little bit differently. So I know I can get 600 out of there. So that goes in there. 6 times 100 gives me 600. Subtract that out and get 126. I know I can get 2 groups of 10, so I can get 20 out of that. So that's 120. And subtract that out, and then I can get 1 group of 6. And notice when we add up all those numbers, I still get 121. Now all of this is in preparation for what we refer to as the standard algorithm division. This is what we're used to seeing. Again, just different ways to get the students to concretely see why this process works. So the way we would approach this, 6 goes into 7 one time. Drop that down. 6 goes into 12 twice. Drop that down. 6 goes into 6 once, and so we get 121 that way. So that's typically how we're used to seeing it. But these other methods are what got us to this point.